Hello everybody. In this video we're gonna solve one example in the textbook named the Aspen Plus Chemical Engineering Applications. It's example 613 in page 181. The reason I'm solving this example is that I got questions about this example from one of the audiences who couldn't solve it or had problems with following up with it. Actually, I checked the example and found that it contains some parts or some details that we didn't go through in the previous videos, about the reactions, and it was covering the sensitivity analysis in more details. So it's kind of going in deep into the sensitivity analysis. So I thought it's a good idea to do the example as a whole. And I'm gonna highlight the parts that are new so that you understand where are the points that I want to highlight. Anyway, so the example is about the synthesis of methanol from carbon monoxide and hydrogen, and carbon dioxide and hydrogen reaction, like these two reactions that we see here, reaction 612 and 613. And there is a side reaction which is 614 that is kind of reaction with between carbon monoxide and the water vapor that's coming out of the second reaction, giving carbon dioxide and hydrogen. So the aim of this example is first to test the synthesis of methanol under equilibrium conditions using rigorous CSTR model. This sentence is kind of not very doesn't make sense according to what we mentioned before, because we know that with the gas phase react, these are all gas phase reactions. It has to be done in PFR, and here it says that it's done in a CSTR, and it's mentioning that the synthesis is done under equilibrium conditions. So we will discuss why we're going to doing the reactions in a CSTR, and what is this sentence, the under equilibrium conditions. I know that the reaction is going to take place at 500 Kelvin and 50 bars, and I know the feed flow rates of the three components, carbon monoxide, carbon dioxide, and hydrogen, which are the three reactants, is 33 kilomole per hour each, so the total is 99 kilomoles per hour. As I said, the reaction is going to take place in a CSTR with a volume of 5 meter cube. So this is going to be the first step, is to do the reaction. The second is to kind of optimize the conditions. First, to change the temperature and pressure to maximize the methanol production. So this is going to be the second part. The third part is to change the flow rates of carbon dioxide and hydrogen to maximize the selectivity of methanol, which means that I want to make sure that the methanol, the amount of methanol to the amount of carbon dioxide is maximum by changing the flow rates of carbon dioxide and hydrogen, and I'm keeping the carbon monoxide flow rate constant. So let's go step by step. First, I define the components here in the properties environment, and for the methods I chose the PSRK. So we have polar components here like methanol and water, but I cannot use an activity coefficient model because I'm operating at high pressures. So I use the PSRK, like what it was done in the example, and I use the steam MBS for the free water method. So regarding the properties environment, there is nothing new. And now let's go to the simulation environment. So for the simulation environment, as I mentioned, I have here the CSTR, the feed. I think I changed something, so it should be 500 Kelvin and 50 bars. And the flow rate is 33, 33, 33 for carbon monoxide, hydrogen, and carbon dioxide. Regarding the CSTR, the pressure is going to be 50 bar, the temperature 500 kelvins. It's a vapor only. The pressure is, or the volume is 5 meter cubed. Again, this is kind of very simple thing. Now let's go to the reaction, because there is something new here. So first, regarding the stoichiometry of the reaction, there is nothing new. I'm gonna define the stoichiometric coefficient of each one of these components, and it's kind of something that we did many times before. But when we go to the reaction here, I couldn't find any information here about the kinetics of the reaction. The only information about the reaction is that it's done under equilibrium conditions. And by doing this, we can find that there is an option here to either go for kinetic reactor or kinetic reaction or equilibrium reaction. For the kinetic reaction, if we choose the kinetic reaction, we'll find that this tab is active, and you should fill the information about the reaction kinetics, either it's Power law or Langmuir-Hinchelwood or whatever the reaction kinetics that you choose. But in this case, we will go for equilibrium reaction, and if you go for the equilibrium reaction, you cannot put any exponents, because the exponents is used for the reaction kinetic equation, but we do not have any exponents here because we are not doing any reaction kinetics. By choosing the equilibrium, I'm telling the software that I want to or I want the reaction to go until it reaches equilibrium. So there is no time related thing. It's all related to the equilibrium conditions or the equilibrium conversion that I will reach. So this is why I couldn't find any information or there were no information provided about the reaction kinetics. And as I said, the kinetic tab is all inactive. And for the equilibrium, you can find the three reactions here. And you mentioned which phase that you want the reaction to take place in. So we're gonna go for vapor phase reaction, and here it gives you an option to put like a temperature approach to equilibrium. It says here that it's added to the reactor temperature while computing the equilibrium constant. So let's say I'm doing or performing the reaction at 500 Kelvin, and I know that in actual process that I can never reach the equilibrium conversion. So there is an equilibrium conversion at 500 Kelvin, but I can tell the software that I will do the reaction or the equilibrium will be reached at another temperature, so that I have a difference between the equilibrium conversion that I'm going to reach and the actual equilibrium conversion that I will reach at the reaction temperature. So I can put any number here. I'm gonna keep it as it is here now. And now you can have the option to compute the equilibrium constant either by yourself, or the software will get it from the Gibbs free energy. So if you choose this option, then you do not need to do anything more. It's going to be calculated automatically. Or if you go here, then you can put an equation that is going to be used to calculate the equilibrium constant. So I don't have this relation, so I'm going to go for this. There is one information or one detail that is important to notice here, that when you go for equilibrium reactions for rigorous reactor, it can be performed only in CSTR. So, and this is the reason I'm doing the gas phase reaction in a CSTR, because the equilibrium reaction cannot be done in a PFR. The reason is not mentioned here in the help, but my intuition is that the equilibrium reaction is one-step reaction. You let the reactants in the reactor, and they will reach the equilibrium once they are there. So this can fit with what was it, the lumped parameter system like a CSTR, but for a distributed parameter system like a PFR, it's not gonna work. CSTR, the PFR is gonna be separated into parts, and each part is gonna be used to do the reaction and do integration, and the output of the first part is gonna be used as the input to the second. Everything is gonna be done in the first part, so there is no way you can repeat the whole thing in the rest of the reaction or the reactor. That's why I think that this is why we can do this only in CSTR. So this kind of explains why it's done in a CSTR model. Anyways, I have tried to do this in a PFR. The same three reactions here, their equilibrium. I did it in a PFR, and this error message showed up. It says that the error that our plug exited because integration failed. The probable cause is incorrect kinetics. So in case you do not have the correct kinetics, you cannot use the PFR. And by the kinetics, we are using equilibrium, so we're not using kinetics at all. Anyway, so I'm now done with defining everything, and for the reactor, I have already defined the reaction set that I already defined before. So now we can run the simulation and see what we can get out of it. So for the results here, we can see how much methanol we got out of the reaction. We have the fate 33, 33, and 33, so I have 99 moles, and the methanol that got out of this is 10 moles. So I'm getting like 10 moles out of 100 moles of feed, which is a very, very small amount actually. So this is one reason or something to tell us why we do the sensitivity analysis and why we need to maximize the methanol production, because at the end of the day, I'm doing this whole reaction to get this product, which is going to be sold as a product with the value. So if I can maximize this amount, I'm maximizing my profit. So this is the reason why I need to do this. I'm gonna do the first part is the sensitivity analysis on the temperature and the pressure. So I'm adding one analysis, and here I'm gonna vary the temperature and the pressure. The manipulated variable is the block variable, which is the CSTR. The variable is the temperature. The range that we used in Kelvin was from 450 to 550 with the 10 kelvins increment, and now I'm adding a new variable here, which is again a block variable, the CSTR. The variable is the pressure, from 15 to 75 bars, the increment of 10. Oops. Of course, I can add as many points as I want, but just to make it easy for me and for the software, it's better to put smaller amount of points that will give you the trend of the parameter changes without using a lot of computational power. There is a probability that the software may crash or something would happen, so you do not need to go through this. And now for the variable is gonna be the methanol flow rate, so it's gonna be CH3OH molar flow in the product. So this is what I'm gonna do. And for this, it's gonna be stream variable. It's gonna be mole flow for the product, and the component is methanol. And this is all I need to just fill the variables, and I am ready to do this. One thing here that is different from we did before is that I am using two manipulated variables, and this is something that we didn't do before. Each time we did the sensitivity analysis, we changed one variable and we tracked the effect of this variable on another parameter. But here I have vary 1 and vary 2. This is something that we didn't see before. And as you see here, it's the way the sensitivity analysis is done is by keeping the value of the first variable constant, like what it is here in the first 7 rows, and it's changing the second parameter while keeping this constant. And after doing all the values of the second variable, it's changing the first variable again, and then doing the same for the second variable, and so on. So I have now 77 runs, and it's giving me also the original run that I did here, which is the very first one in the conditions I used to operate the reactor before the sensitivity analysis. So this is good, but I need to kind of see this as tabulated results or as a graph. So when I click on the results curve, it gives me this window that is giving me some options. The first is how can I display the two variables? One of them can be put as the x-axis parameter, and the second is what's called the parametric variable. So I'm gonna keep it as it is, and I'm gonna show you in a minute what I mean by this parametric variable. And the curves to plot is gonna be the methanol production or methanol in the product. So as I mentioned, the x-axis is gonna be the variable one, which is the temperature. Then the second is what the parametric variable is each one of these lines. As you see here, the variable 2, the CSTR pressure 15, so this is 15, 25, 35, 45, 55, 65, and 75. So this is what I mean by parametric variables. I can flip it by putting the x-axis as the pressure and different lines. Each line represent a different temperature, so it's up to you. And here you can see that this is the point that I'm using to operate the reactor right now before the sensitivity analysis, which is at pressure of 50 bars at the temperature of 500 Kelvin. From this we can see that the reaction is favored at lower temperature. So as I'm going at higher temperature, the methanol production is reduced, or the flow rate of methanol is reduced at all pressures. And I can see that at each temperature it's better to operate at higher pressure. It's clear that the methanol produced at 15 bar is less than, or it's total, or it's a big difference from what I have at 25, and the difference is getting smaller as I'm increasing the pressure more. But the maximum point that I can find here is this, which is 75 bars and at the 450 kelvins. So these are gonna be the operating temperature and pressure that I'm gonna use to operate the reactor to maximize the methanol production. However, I do not know how much or what's the selectivity that I have, how much of the reaction is going to produce methanol and how much of the reaction is going to produce or going to the side reaction. That's why I need to create one more sensitivity analysis, which is gonna be called S2. And here I'm gonna change the manipulated variable. It's gonna be the mole flow of the feed, and the component here is gonna be hydrogen, and I'm gonna go from very small amount from 1 to, like, I'm gonna go to very high 101 with increment of 10. I cannot go for 0 because 0 is gonna give errors, so I'm not gonna, I don't like to go through these errors. So it's better to go from very small value up to very high value. And I'm gonna do the same for carbon dioxide. So for variable number 2, it's gonna be mole flow for the feed of the component CO2. Again, I'm gonna go from 1 to, like, I'm gonna go to 71. And I'm gonna do the increment of 10. I'm using here 71 while I used 101 for hydrogen, because I know that it's better to maximize the amount of hydrogen and to minimize the amount of CO2. But this is from my knowledge, but because I solved it before, and because this might be something that we can expect here. From the results of the first run, we saw that the carbon dioxide amount was not changed a lot. We can check it again for the stream results of the CSTR. The carbon dioxide was like slightly consumed. It was 33, and only less than 0.2 moles were consumed, or kilomoles per hour were consumed. So I know that the carbon dioxide consumption is not that much, and the majority of methanol is coming from here. So my intuition is telling me that even if some methanol or carbon dioxide is consumed here, it's gonna be produced here to compensate that loss. So I prefer to not increase the CO2 and kind of depend more on the very first reaction on the production of methanol. This is my intuition based on the results of the first run. You can depend on it while doing the sensitivity analysis, or you can do it for the whole range, if you like. It's up to you. And for the variable here, I want to calculate the selectivity, and the selectivity is the amount of methanol divided by the amount of carbon dioxide. So I need to do this in Fortran. So to do this, I need to define the variables that I'm gonna use in Fortran. So the first is the methanol mole flow in the product, or you can use mole fraction. It's up to you. And I'm gonna do the hydrogen or CO2 mole flow in the product as well. The first is gonna be stream. And the type is going to be mole flow in the product, and the component here is going to be methanol, and the second is going to be the same but for CO2, so it's stream mole flow of CO of the product, and the component is CO2. And here in Fortran, I'm gonna calculate the selectivity, which is, of course, you need to put the variables here with the same spelling. So there is a probability that you might forget the spelling or have a typo. So to prevent this, I'm gonna close it and redo it again. So right click here and click on variable list, and you can drag and drop instead of having any issues with writing the names. And here I'm gonna get this, and this is all for Fortran. And for tabulate, I'm gonna fill variables, and for column number 3, it's gonna be the selectivity. So that's all, and now we can run the file, and we see what are the results of the sensitivity analysis that we get. And as you see here, we have all the combinations for the variable 1 and variable 2. And again, I have here the selectivity first was 0.3 because it was 10 over 32, so it's almost 0.3. And we see that there are values that are much higher. I have 25, so there are values that are much bigger. Again, I want to see this as a results curve. I want to have the carbon dioxide as the X value and the hydrogen as the parametric variable. I'm not interested in these. I'm interested only on the selectivity, and this is what we see. So there are many outputs that I can get out of here. The first one is very obvious, that the carbon dioxide flow rate, as the carbon dioxide flow rate increases, the selectivity drastically decreases, starting here from 11, or I think this is 11. We have the values are very, very small, and it's very hard to differentiate between the values. And this is the point, this is the point, which is this square is the point while I was operating, which corresponds to 0.3. So all the values here are very, very small, regardless the amount of hydrogen. There might be some differences here, but they're not as high as they are here. So this kind of confirms my observation that the carbon dioxide is not favored in this reaction, and it's not gonna be helpful to maximize the methanol production. The second here is that I have, this is the hydrogen 1, hydrogen 11, hydrogen 21, 31, 41, 51, 61, 71, and up to 101. And the maximum value is at 101. So it's clear that as we increase the hydrogen amount, we are maximizing the methanol production. It's gonna be good until we reach a point where all the carbon monoxide is consumed, and then we will not have any more reaction. So it's not gonna increase the selectivity of methanol. So at some point we'll have overlapping lines here. So from this we can get the output that it's better to operate at very low carbon dioxide flow rates and very high hydrogen flow rates. The way it's done in the textbook is kind of different, and has been using some kind of different equations that I'm using, and he was doing this in a more complex way. But I personally got the same outputs without going through this, so I think you can do the same thing I'm doing. There is one thing also that I need to mention here is that the numbers I'm getting are different from the numbers that were produced here in the solution in the textbook. These numbers are totally different from what I got. I tried all the different combinations of variables changing and the settings, but I never was able to get the same outputs. But anyways, the results are of the sensitivity analysis as output for the operation of the reactor are the same. So I'm happy with it now. So from this again, I'm getting the output that should give me the maximum amount and the highest selectivity for methanol production. So I'm gonna do this for the CCR and test it. So I'm gonna operate at 75 bars and at 450 kelvins. And for the feed flow rate, I'm gonna change it from 33. This is gonna be 101, and this is gonna be 1. And now let's run and see what will be the difference in the methanol production in the CSTR. And for the mole flows, you see that I am almost totally consuming the carbon monoxide. I have only 0.11 moles from the 33, and I have 33.4, almost 0.4 kilomoles per hour of methanol, corresponding to 10 point something that I got before. So I kind of have 3.3 times the amount of methanol that I was producing before. So this is kind of gives us an idea how we can improve the conditions or improve the production of the output that we want from a reactor, and this can be applied to any other unit in Aspen Plus. One thing I want to mention before finishing this video is that this is the optimum conditions according to the process operating conditions. So there are other perspectives that might change the operating conditions. For instance, the economic perspective to operate at this temperature and pressure might cost you more money, and this money might not be feasible. Like you are gaining more money by selling the more methanol that you are producing, but at the same time, this money that you are gaining might not be enough to cover the expenses of increasing the pressure. So this is something that that might affect the operating conditions. One other thing is that you might not be able to control the flow rates of the feed, and controlling the feed flow rate might affect the economic feasibility of the process. That you cannot or you need to do a separation unit first to get rid of carbon dioxide and then go into the reactor. So this might not be feasible as well. So this is again from the process point of view. The rest of the parts might be more effective on the decision according to the feasibility of these conditions. So I hope it helps, and I hope it's clear, and I'll see you in the next video, inshallah. Goodbye.